Do you remember titrations? We've actually done a couple of titrations, right? We did a redox titration on our green salt. We're going to review acid-base titrations. So, when we have an acid-base titration, we have a solution with a known concentration. That's what we usually put in the burette. And we react it with a solution of an unknown concentration, and that's typically in an Erlenmeyer flask. Right? So one of them is an acid and one of them is the base. In general chem, most of the time we're taking sodium hydroxide as the known concentration, and we're finding the concentration or the amount of the acid. As we add that known solution, we're going to keep an eye on the pH, either using an indicator like phenolphthalein that will change color and alert us to the change in pH, or we can use a pH meter and actually measure the pH. So the equivalence point is, equivalence means equal, right? That's where the moles of acid is equal to the moles of base, stoichiometrically. So the stoichiometry, remember, you could have a 1-to-2 ratio, a 2-to-1 ratio, depending on what your acid and your base are. When you get to the equivalence point where you've added the stoichiometrically correct moles of, say, your base, completely neutralized all your acid, then you can calculate the concentration of the unknown solution. Does that at least sound familiar? You can nod your head like this, or shake your head. This means no, this means yes. Come on, everybody, do it. Okay, you are listening. Pictures. Here we have a burette with a base in it, hydroxide, and we have an acid here in our flask. An actual photograph, it's going to look like that. It looks like we're adding water to water, right? As we add some of the sodium hydroxide, or the hydroxide, it's going to react with the hydrogen ions in our acid solution and produce water. What we see as we're titrating is we may see a little bit of pink, and then it disappears. We see pink here because as we add the hydroxide, it doesn't mix instantly with everything. And so we momentarily have a higher concentration of base right here, but when we swirl it, it all goes away. At the end, at the equivalence point, we've added enough hydroxide to neutralize each of the hydrogen ions in this solution, and that's when the color will change. Now, that's a really dark endpoint, but we can see it in the picture. It's actually really close to my favorite color. People ask you, what's your favorite color? Phenolphthalein pink. What? What the heck? You don't see that in Yetis. Okay, that was review of titration. So we can make a titration curve or a pH curve. This is a plot of the pH of the solution versus the volume of the known solution added. So if we're titrating a strong acid with a strong base, titrating maybe HCl with sodium hydroxide. We start out, we measure the pH of the acid solution. It's low, as expected. As we add base, the pH goes up. It doesn't go up very much, though, because we're neutralizing the acid, but the base is not left in there. It gets neutralized. When we get to the equivalence point, the pH changes very, very rapidly. The shape of this curve depends on a lot of factors, including the acid strength and the base strength, but that's sort of a generic shape of a titration curve. Okay, this is where millimoles is really going to be helpful. So, millimoles. Chemists are often measuring volumes in milliliters, right? Because a liter is a lot of stuff. a milliliter is a more useful quantity, and so, it's like, oh, well, I added 10 milliliters. So what we end up doing then is a lot of conversions from milliliters to liters and then back to milliliters again. And by using millimoles, we can avoid that. The other thing that happens here is when we get these amount in moles, they are really small, too small to express in decimal notation. So they'll be like 0.00004. And so then we end up having to use scientific notation. It's just kind of a pain. So millimole, abbreviated MMOL, takes care of both of these problems. So a millimole is 10 to the minus 3 moles. Milli can be applied to any unit, just like 1 millimeter is 10 to the minus 3 meters. That's all it is. So when we have our molarity, abbreviated capital M, that means moles per liter. But we could also write that as millimoles per milliliter. This is the same because we could cancel out the millis and it's still moles per liter. Everybody cool with that? It's the same thing. So we see capital M, we can write moles per liter, we can write millimoles per milliliter. Just depends on what we're going to do with it. So, consider the titration of 25 milliliters, there's the milliliters, of 0.1 molar HCl with 0.1 molar sodium hydroxide. And we want to find the volume of sodium hydroxide needed to reach the equivalence point. Chem 1A calculation. So titrations are stoichiometry. And so we should always have the balanced chemical equation either written down or on the whiteboard in your mind. Okay? A lot of them are 1-to-1, but not all of them are. And so it's really important to know that. So what I like to do for stoichiometry is I'll take the information up here and I'll write it under the equation to kind of organize it. So I have 25 milliliters of the HCl. Oops, gotta select the pen first. So 25 milliliters of that. And they're telling me what the concentration is. That's the HCl. Now, it says capital M. I'm going to be using this as a conversion factor, so I don't want to use the capital M. I want to write what it means. And so it means moles per liter, but here I've got milliliters. So I'm going to write millimoles per milliliter. And then we're told the concentration of the sodium hydroxide. Sodium hydroxide is also 0.1, and that can also be written as millimoles per milliliter. Any questions yet? So, titrations are stoichiometry. Stoichiometry is dimensional analysis. And so for all stoichiometry problems, what I teach my students to think of is grams to moles to grams. That's the starting point. So you just remember grams to moles to grams. We always have moles in the middle, like that TV show Malcolm in the Middle. We have moles in the middle. There's always going to be the moles in the middle. So we think grams to moles to grams, and then we see, well, does that work for this problem? Do we have grams to start with? No, we don't. We have milliliters. This is the one we're starting with because we have more information. This is the one we're trying to find out something about. We're trying to find its volume, question mark. It doesn't say what unit, but we often use milliliters in chemistry. So instead of grams, I'm going to start with milliliters. Milliliters of HCl. I can convert that to moles of HCl to moles of sodium hydroxide, and then do I want mass? No. I want milliliters of sodium hydroxide. So this is my path, my guide for writing out the equation. So 25 milliliters of HCl. So milliliters to moles to moles to milliliters. So moles of HCl, moles of sodium hydroxide, milliliters of sodium hydroxide. You don't have to write this part down, but again, you should at least put it on the whiteboard in your mind, right? Milliliters to moles to moles to milliliters, those are the units that go on top of all these fractions. It's telling you what to write down. This is the hard part, figuring out that. Now, we just need to put some units in to cancel all these other guys out. So if I want milliliters of HCl to cancel, I need to put it in the denominator. Milliliters, milliliters of HCl. Cancels. But do we know moles per milliliter? We know moles per liter or millimoles per milliliter. So let's make this millimoles. To cancel millimoles of HCl, we're going to put millimoles of HCl down here. And now this unit needs to be adjusted too. And then over here, millimoles of NaOH. Thinking about it, it might be more straightforward to look at this path and say, oh, I've got milliliters to moles to moles to milliliters. I should just use millimoles in here, and so just write that M in the milli in here. And then when you come down here, you don't have to think about it. That's probably better. I'll explain it that way tomorrow. Do you see how the units work out? It's beautiful. Very little thinking once you figure out the path. So now that we have all the units in, we put the numbers in. Dimensional analysis is analyzing the dimensions, the units. So we use the units to tell us what to do, and then they tell us where to put the numbers. We don't have to remember I'm supposed to multiply by this and divide by that. We just look at, well, what do the units want me to do? So the relationship between millimoles of HCl and milliliters of HCl. Well, that's this guy right here. Did I leave enough space for it? No, I did not. That's okay. We'll just sneak it in here. 0.100. That was given in the problem. Millimoles to millimoles, or moles to moles. That's where the stoichiometry comes in. We look at the balanced chemical equation. Here, there's an understood 1 in front of HCl, an understood 1 in front of sodium hydroxide. So it's 1 to 1. And then at the end, we have millimoles and milliliters of sodium hydroxide, and that was also given to us in the problem. 0.100. Did I do that right? No. Again, I wish I could say I did that on purpose. But here's where the units help us out. Is it 0.1 milliliters per millimole? No, this number is supposed to be down there. And I just had a little brain fart there and put it in the wrong place. So put it down there where it belongs. Any questions? On your calculator, you just start at the left and you go to the right. So 25, multiply by the top, divide by the bottom, multiply by the top, divide by the bottom, multiply by the top, divide by the bottom. Oh, well, there isn't a number there. Well, it would be a 1, right? And there's no number down here. If that bothers you, write the 1 in. Of course, multiplying and dividing by 1 doesn't change anything. So if you want to skip that part and just do this, times 0.1 divided by 0.1, that's fine. If you want to do all the ones in because that's the way your brain works, I know I just need to do all the things, then do all the things. We'll all come up with the same answer. We're going to end up with 25 milliliters of sodium hydroxide. Any questions? You learned how to do this in Chem 1A. I've reviewed it for you in some detail, how to do the calculations. I am going to assume that you know how to calculate this from now on. If you don't understand, don't remember, never clicked in 1A, please come and ask me, and we can get it to click, and then it'll be just easy peasy. So we're going to think about a titration of a strong acid with a strong base. And so we're going to use that thing that we just were calculating. So we have 25 milliliters of 0.1 molar HCl. We have 0.1 molar sodium hydroxide. And so we are going to calculate the points for a titration curve. So first of all, we need to know what's the initial pH. This is before we add any base. Well, what do we have here? We have 0.1 molar HCl. What kind of an acid is HCl? It's a strong acid. If we don't remember, it actually tells us right up there. So 0.1 molar HCl, a strong acid, ionizes completely. And so that will give us 0.1 molar hydrogen ions and 0.1 molar chloride ions. pH, negative log of the hydrogen ion concentration. The negative log of 0.1 is 1. Any questions? That should also be pretty straightforward. Strong acids are a lot easier to deal with than the weak ones because there's no equilibrium to mess around with. That's why we're starting with the strong acid. Okay, so they graphed that point for us. At 0 milliliters of sodium hydroxide added, the pH is 1. Now, we're going to look at what's the pH after we add 5 milliliters of sodium hydroxide. Well, this requires stoichiometry. So we're going to use our moles initial, change, moles after, MICMA. I think my husband calls it a Mickey Mouse, but we're going to use this kind of table. So this is what we did looking at the buffers, right? So here we have the hydroxide being added. So 5 milliliters of 0.1 molar hydroxide. Where do they get this 0.5 millimoles from? 5 milliliters times 0.100 millimoles per milliliter, 0.500 millimoles. No converting, just multiplying. Milliliters times molarity gives us millimoles. So we've added millimoles. Remember, in these stoichiometry tables, we have to use moles. We can't use concentrations. What amount of acid did we start out with in millimoles? Well, we had 25 milliliters of 0.1 molar. 25 times 0.1 is 2.5, right? 2.5 millimoles. So those are our starting amounts in moles. You have to do a little calculation there. On this one, they're not just giving us 1 liter like they did with the buffers, giving us more realistic things. So here we have a stoichiometry problem. It's basically limiting reactant. Which one is less? Well, we have less of this one. So we're going to assume complete reaction. We're going to react all of this so that that goes away. And then we're going to end up over here by subtracting the 0.5, we're going to end up with 2 millimoles of hydronium ion. Well, we want the pH, we need a molarity. Here's our 2 millimoles. We have to divide by the new volume, because when we add 5 milliliters, we change the volume. And that's why we have to do these in moles or millimoles instead of molarity, because the volume keeps changing, so the concentrations keep changing. So here's our millimoles of H3O+, and we're going to divide by the new volume. That's the volume that we started with, plus the volume that got added. Everybody see that? So you do the math there, you get 0.0667 molar. And then we can calculate the pH. pH, negative log, 0.0667. .1759. Everything here has 3 sig figs, so I'm going to go with that and call this 1.176 as the pH. Any questions? So they graph that point on here. It's only gone up a tiny bit, right? Because there's still a lot of acid in the solution. So we can calculate the pH after adding 10 mils, 15 mils, and 20 mils of the sodium hydroxide. The good news is I'm not going to do all 3 of those. I'm just going to do 1. So previous slide, we had the table all written out for us. Here, we don't have the table, so this is what we're going to do. So we've got HCl and NaOH. We've got the H plus and the OH minus. So we're adding hydroxide. Just blanked. Yeah, okay. We're adding hydroxide to an acid. Whoops. And this is going to make water. And so we're doing moles initial, change, and moles after. It's mikma because mikmuf is harder to say, so it's after instead of final. How many millimoles of hydroxide have we added? Let's do the 15. How many millimoles of hydroxide have we added? Well, we have to do a little calculation there, right? 15 milliliters of sodium hydroxide times 0.1 moles per liter sodium hydroxide. Remember, this could be millimoles per milliliter. So that's going to give us 1.50 millimoles. Okay? So we're going to have 1.5 millimoles of that. How many millimoles of hydrogen ion or hydronium ion did we start out with? We're going to do each of these calculations as if it's the only thing that's happened. We're not going to look at what the 5 milliliters and do anything with that. We're just going to look, if we started out and just added 15, what would happen? Well, so we still have this 25 times 0.1, the 2.5 millimoles of acid initially present. Okay? That's how much was initially there. Now we've added a total of 1.5 millimoles of hydroxide. This is the smaller one, so we're going to subtract that, and our hydroxide is going to be approximately 0, and we subtract 1.5 from the acid, and this gives us 1.00 millimoles of H3O+. You follow that okay? So we need the hydrogen or hydronium ion concentration. Well, it says hydronium there, so let's write hydronium. Good grief. 3. So that's going to be the millimoles of hydronium that we have left divided by the new volume. We started out with 25.0 milliliters, and now we've added 15 milliliters. Be careful when you do that on your calculator. .025 molar H3O+. pH, negative log of 0.0250. One 1.600206, 1.602. So that's this point right here. Any questions? Do you see what we're doing here? We're just looking at the simple reaction between hydroxide and hydronium. We're looking at how many millimoles of each we started with, and then we're going to see, well, they're going to react, so the smallest one will get all used up, and the other one will lose the same amount. That gives us the millimoles that we end up with, but to get the concentration, which is what we need for pH, we have to divide by the new volume. So this denominator here throughout the titration is continually changing. Okay, so let's see what happens when we've added 25 milliliters of sodium hydroxide. This is at the equivalence point. So we have hydroxide plus hydronium. It's making water. Moles initial, change, moles after. 25 milliliters of 0.1 molar, how many millimoles of sodium hydroxide is that? 2.5, right? We got 25 milliliters times 0.1 molar is 2.50 millimoles. So I've added 2.50 millimoles of hydroxide. How much hydronium ion or hydrogen ion did I start with? 25 milliliters of 0.1 molar. Also, .5. So these are equal. So what we end up with is both of these being approximately 0. Well, we can't take 0 and divide by the new volume and get the concentration of hydrogen ion, right? Is it actually 0? No. We have completely neutralized it, so now we have water, right? What's the concentration of hydrogen ion in water? It's equal to the hydroxide, and it's 10 to the minus 7. The pH is going to be 7.0. So this one could be a smidge tricky, right? Because you subtract these and you end up with zeros, and then you're like, what? We've gotten rid of all the HCl and all the NaOH. They've canceled each other out. What do we have left? We have the water that they're swimming around in, pH 7. So on the graph, that's up here. And look how from 20 milliliters to 25 milliliters, the pH jump was huge. That happens. Any questions? What if we keep going? We didn't do this when we were just using indicators, because what's the point? But if we're measuring the pH with a pH meter, we can keep going and see what happens to the pH. We can also do the calculations. So let's look at the pH after adding 30 milliliters of sodium hydroxide. 30 milliliters times the concentration of 0.1 gives us 3 millimoles. We have our initial amount of acid was 2.5. So now we see that the acid is the limiting reactant, and so this will end up being 0, and this will end up being 0.5 millimoles of hydroxide. So we can calculate the hydroxide ion concentration. It's going to be 0.50 millimoles divided by the new volume in milliliters. So we started with 25, and now we've added 30. .009090909. It just kind of goes on 09. It's kind of cool. We want the pH. Remember the circle of pH? Hydroxide ion concentration and pH are on opposite sides of the circle. I like going through POH because I think the math is simpler. Let's calculate POH for this. That's the negative log of the hydroxide ion concentration, negative log of 0.009090. So POH 0.04139. And then we remember that pH plus pOH equals 14. So the pH will be 14 minus the pOH. $11.9586. Here, this guy's down to 2 sig figs. So that's going to be 11.96 for the pH. And so they've graphed that point up here. It's very close to 12. Any questions? We're going to do the same process with weak acids and with weak bases. And it gets a little more complicated. So we're starting with strong acid, strong base. If you can see in your mind what's happening here, then coming up with remembering how to do these calculations isn't that bad. It's like, oh, well, I've got this, and this kind of knocks out that, so I've got this much left over. I need to figure out my new volume, so I get that concentration. Now I can find the pH. So it's important to understand this one because the next ones are going to get more interesting. So we can also calculate the pH after adding 35, 40, and 50 milliliters. I'm pretty sure you don't want to see me work that out. That's fine. So we could calculate those, and after you've recovered from the exam, maybe go through and try to do these guys on your own, see if you can come up with those numbers. So what we end up with overall is here's our initial pH. This part down here, it's not horizontal, but it's pretty close. This is before the equivalence point. That's where we have an excess of hydronium ion. So the pH is low. At the equivalence point, when we titrate a strong acid and a strong base, the pH is going to be 7. After that, we've got additional hydroxide, and so the pH goes up. And this is the overall curve for a strong acid, strong base titration. Any questions? If we titrate a strong base with a strong acid, the curve is very similar. The calculations are very similar. What's the obvious difference here? It starts high and goes low, right? Whoops, wrong button. This one starts low and goes high. The equivalence point is still at 7. So I'm going to leave this problem for Monday as kind of a segue over the weekend.